Okay, we'll get started in about a minute. A minute. All right, here we go. Homework corrections 1 through 18. Oh, am I on the right thing? Was it 1 through 18 all? Just make sure I have both. Yeah, no, that's the right one. Okay. 11.3, 1 through 18 all, page 436. So 1 through 8, we're all a table. Number 1, A is 70 units, M is 10 units. And remember, A would be an area, so 70 units squared. Number 2, A is 30.5 square units, M is 5. Number 3, A is 6 square units, M is 3 3/4 if you wrote it as a mixed number, or what, 15/4 as units as improper fraction. Number 4, H is 10 units, M is 30 units. Number 5, H is 5 units, M is 18 units. Number 6, base 2 is 5 units, M is 4 units. Number 7, base 2 is 1 unit, and M is 4 units. Number 8, base 1 is 15K units, and M is 9K units. Number 10, 64 square units. Number 11, 108 square units. Number 12, I think we did this one in class, 21√3 square units. Number 13, oh, this was an ugly one, 27√3/4 square units. Number 14, I know that we did this one in my advanced class, 94.5 square units. Number 15 is 24 square units. 16 is 180 square units. 17 is 128 square units. And number 18 is 65 square units. Hey, make sure you're turning this stuff into teams. We only have a few things in the grade book, so missing one really affects your grade a whole bunch. Brianna, make sure you turn in your course selection sheet. Okay, we're going to finish up today, 11.4. We're probably going to forget many of these things, so we'll make sure after spring break we do a review day. I'll review everything 11 through 4 on that day, and then we'll move on. 11.5, then we do, I think it only goes up to 11.7. So we got a while before the test. No quiz. I didn't want to have a quiz because of spring break. So we'll just jump right into that test. Here is your homework for tonight. Oops, sorry. There is your homework for tonight. I would knock this out immediately. I wouldn't wait to the end of spring break because then you'll forget everything. Remember, if you do choose to do that, however, remember you can always re-watch this video to give you help on this. Page 443, 1 through 12, all. 443, 1 through 12, all. Here we go. All right, so area of regular polygon. So every one of these sections, 11.1 through 11.3, we dealt with a different shape. And now all of a sudden we get every single shape that's out there. Turns out that this is a pretty slick class. You'll see why in a second. All right, one thing today, it's actually pretty easy. It's one little tiny formula. You saw this one in 11.1, and I said, hey, here's a formula that you're going to encounter. You just haven't seen it yet. And today we get to see that formula. It's pretty easy. Think about this. Polygons. We've been doing areas of polygons, squares, triangles, trapezoids, parallelograms. These are closed plane figures constructed of segments joined at their endpoints. For instance, a triangle is made up of 3 segments where the segments have been joined at their endpoints, and it's closed. You can't get to the inside of the shape without crossing over a segment, and it's flat, so it's on a plane. Regular polygons, a type of polygon, is a polygon where all the angles have the same measurement and all the sides have a same measurement. For instance, the equilateral triangle. An equilateral triangle is a regular polygon because all the angles are the same number. Look, all three angles are 60 degrees, and all three sides, for instance, might be 10 centimeters. The key here is not that the angles are the same number as the side length, right? One's 10, one's 60, but all the angles are the same number and all the sides are the same number. That's what makes it a regular polygon. Today's class is only on regular polygons. Okay, so no irregular shapes. So it turns out that regular polygons, right? Here's the triangle, here's a square, here's a regular pentagon, here's a regular hexagon, regular septagon, regular octagon. All of these can be inscribed inside of a circle. All of them can be inscribed in a circle. Now, that's not true for all polygons. For instance, here's a pentagon that is not regular. And notice there's no way to inscribe that pentagon inside of a circle. Well, if we make it, notice here, here's the pentagon right here. Notice if it's regular, boy, does it fit nicely inside of a circle. But as soon as I make that pentagon irregular, as soon as I make it irregular, it can't be inscribed. Remember, the definition of inscribed is where all the vertices of the polygon, this one, and this one, will touch the circle itself. And notice for this one, I can only get 3 of the sides to touch it. There are a couple of exceptions, 2 of them precisely, and the ones that could be irregular and be inscribed are a rectangle, and any triangle can be inscribed. Remember, that was one of our constructions. But besides the rectangle and the triangle, if you have an irregular polygon, such as a hexagon, octagon, dodecagon, if they're not regular, you can't inscribe it. All right, so here comes the new stuff. It's going to come at you kind of fast. I promised you it would be easy, so you just got to hang with me. All right, a couple weird vocabulary words. All right, the first one is going to be called the center of a regular polygon. You're like, well, that doesn't sound too complicated. It's not, but it's new. The center of a regular polygon, so we're going to take a regular polygon, we're going to put it inside of a circle, and if you pick the center of the circle, that will also be the center of the polygon. Okay, so let me give you a picture, make more sense. So if I put a regular, in this case, pentagon, inside of a circle and inscribe it, then the center of the circle is also the center of the polygon. That's all that's saying. Now, this is only true for regular polygons. You put an irregular polygon in here, that's not true. The center of the polygon will not be the center of the circle. Let me see if I can crudely draw that for you real quick. So if we take a circle and draw an irregular polygon right there, notice the center of that polygon is right here, but the center of the circle is right there, okay? But if you make the whole shape regular, then the center of the circle and the center of the polygon are one and the same. Secondly, here comes the first hard and challenging word. It's called the radius of a regular polygon. Okay, so I have a regular polygon, in this case, pentagon. I put it inside of a circle, and the radius of a regular polygon is also the radius of the circle, right? So I need you to make sure that this picture is very clear in your head, is that if we have a regular polygon and we connect the center of the polygon, which is also the center of the circle, and create a radius that will also be the distance between the center of the polygon and any one of its vertices. I just chose one here, but any one of the vertices, I'll draw the other ones here. Any one of the vertices, right, would also be the radius of the circle. Okay. And you're like, well, that's not too difficult. I agree, but there's going to be one more word, one more definition, and between that one and radius, you'll get the two mixed up. All right, we okay to move on, Bree?
Sure.
Okay. All right, last one, or there's two more, I'm sorry. Central angle. Now, we've already dealt with central angle before. Remember, central angle is you have a circle, You go from the center outwards, and we know that this angle right here, I'll call it theta. That angle theta is also the angle measurement of the arc. We've already seen that for central angles before. This is the central angle of a polygon. It's basically the same idea. We take a regular polygon, we make two radii, and what we're talking about, what we're talking about here is the central angle would be this angle right here. So I'll make that theta. So that angle right there would be the central angle of that regular polygon. 2 chapters ago, when we talked about this, then we talked about the arc. We will not be talking about the arc today. What we will be talking about is something, and this is the important one, something called the apothem. Brand new word. I made it red there, but it's called the apothem of a regular polygon. And that is, okay, we got this basic shape that we just drew right here. If you go from the center to any one of the sides of the polygon, I chose that one. That right there, black dotted line, is called the apothem. And here's where the confusion comes in, because we have 3 things now. We have the central angle. The central angle would be this angle right here. We have the radius, that would be the red solid lines here. And then we have the apothem, which would be that black dotted line. Now that black dotted line is one of the apothems. Here's, I better do that in black. Here are the other apothems. So it goes from the center perpendicular to a side, from the center perpendicular to a side, from the center perpendicular to side. All these black lines that I'm drawing are also apothems, okay? As always, it's high school geometry. So notice what I've drawn right here is an isosceles triangle. Why? The 2 red lines here are radii, so they're equal. So basically, we get a isosceles triangle, which will be very useful for us in a second. All right, now since this can cause confusion, I'm going to show you 3 slides, same basic picture, just with everything labeled. So for those of you that are a visual person, right, this is a good one for you. Here is a hexagon, a regular hexagon. I have my center. Let's see, the central angle would be right here. The blue lines are the radii, and the red line is the apothem. So radii go from the center to a vertice of the green hexagon. The apothem goes from the center to the side of the hexagon. So there's one picture. And yes, I'm having 3 simply because I want to drive home the point. So here's one without the circle, right? So from the center of a regular, in this case, hexagon, the radii would be, I think that's, I'm bad with these colors here, pink or purple or something like that. The central angle would be any one of these angles right here, that one or this one. The apothem is the, oh, I should have picked better colors here. Is it orange? Orange. And then the side, of course, would be any one of the green or black sides. All right, I said 3 pictures. There's 2, and here's a last one. So here's a pentagon, radius in red, apothem in purple, sides in either green or whatever that blue color is. Okay. So why am I showing you that 3 different things? Because this is the shapes and the definitions that we're going to be dealing with. Radius, apothem, and sides of the polygon. This is called a proof plan. A proof plan is where you don't want to do a formal proof. You just kind of want to write out some thoughts. It turns out this is a full honest-to-God proof. I'm going to write out everything. We're not going to do a formal proof, but a lot of times if you take higher level math and you want to do a proof, nobody wants to write a 2-column proof. You just want to write a couple thoughts on your paper, see if it works first, and then you can write it out more formally. So this is called a proof plan. And by the way, this is going to be a proof. Take any regular polygon. So for instance, here is an octagon, but it could be any regular polygon. And I want you to consider one of the internal triangles of that regular polygon. For instance, this one. right? So that triangle is made up of a side length of the polygon, right? And it's made up of 2 radii of the regular polygon, okay? So I got side length and I got radii, right? I'm going to label those parts now. So S for side. The apothem, remember, goes from the center of the polygon to any one of its sides. So A for apothem. And then let's calculate the area of this triangle. So the area of any triangle is 1/2 base times height, right? Where our base here is S and our height here is A. So 1/2 SA. Now I would like to figure out the area of the whole shape. So the question is, well, how would I do that? Well, I figured out one of the triangles, and one way of doing this would be to consider, well, how many triangles are there? Well, let's see, there's the one that we just made, 1, 2, 3, 4, that's a horrible line, 4, 5, I'm not doing any better, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So that 8 would also correspond with how many sides there are. All right, so if I wanted to know the area of this octagon right here, I would take the area of one triangle and multiply it by how many sides there are. Well, there's 1, 2, 3, 4, 5, 6, 7, 8. I'm not going to use S because S represents one side. So I'm going to pick another letter. I'm going to choose the letter N, where N represents how many sides. So N represents how many sides there are of this polygon. There's 8 of them. I take that and multiply it by the area of one of the triangles. That would be this black one right here. And then we get the area of the polygon, okay? So so it looks like we got a formula here. N times 1/2 times S times A. And it turns out we can make this one even easier. Erase everything I drew so far. N represents how many sides there are. And what we really want to do is multiply N times the number of sides. So I'm just going to move that N, and I can, commutative property. I'm going to move that N next to the A. That's all I did. So I have NSA. So once again, that sounds like a perfectly fine formula for area. I can make it easier. Watch this magic. Okay, what I want you to think about is the perimeter. Consider the perimeter of this polygon. The perimeter of this polygon would be S plus S plus S. Well, it'd be all of them added together. Well, that would be the same. That would be the same as N times S. Well, N represents how many sides? 8. And if I multiply 8 times S, that would be the perimeter. So the perimeter of any polygon could be written as N, where N represents the number of sides, times the length of 1S. And look what I've written now. So what I've written now, I've written that NS can be written as the letter P for perimeter. So I can take this P and substitute it in for the letters N and S, and I get a really, really, really slick formula. It turns out for any regular polygon, be it a triangle, be it a square, a pentagon, hexagon, octagon, any polygon, that the formula for area is 1/2 PA, where P stands for perimeter and A stands for apothem. So all those other weird formulas that we've done before, if it's applied to a regular polygon, instead of having 46,000 different formulas, we only need one formula. Ladies and gentlemen, there it is. That's it. That's the only formula I need if you have a regular polygon. Now, granted, when you don't have a regular polygon, this doesn't work. But if you have a regular polygon, this is the only formula you need, okay? So here's Theorem 11. Oh, by the way, we just proved that. Theorem 11.6. If you have a regular, remember, I can't stress it enough, it's got to be a regular polygon. If you have a regular polygon, you calculate the perimeter, you multiply it by the apothem, and you divide by 2. So 1/2 PA. Boy, that looks like a triangle formula, doesn't it? 1/2 base times height. This does work for a equilateral triangle. If you have an equilateral triangle, you calculate the perimeter, multiply it by the apothem, divide by 2, you got the area. Very useful. In architecture, construction, generally speaking, we like regular polygons. Irregular polygons look a little weird, but regular polygons look beautiful in architecture, which is why they're always used. And so therefore we got a nice one formula, not 46,000 different formulas. Hey, I got a dodecagon. I got to pull out the dodecagon form. No, you pull out this formula right here, as long as that dodecagon is regular, 1/2 PA. We good, Bree?
I guess.
Okay. Don't say I guess if you mean no. All right. So how does this work? Well, the issue with high school students is that the apothem and the radius, boy, do they kind of look alike, right? There's nothing special about the word radius or apothem. All right. You can mix up the A and the R really easy. Okay. So make sure that you know which is which. The apothem goes from the center to a side, and the radius goes from the center to a vertex. Okay. So let's do this. So before, I'm trying to make a big point here about the fact that we have all these different formulas, right? Up until high school, you've never calculated the area of a hexagon or an octagon, right? And you think that there's all these different formulas, and now there's just one formula as long as it's regular. So I don't know, I'm trying to add some humor here, but there's one formula for them all. All right. Now we're going to do some really challenging geometry work. The formula is easy, 1/2 PA, but we're going to apply that to a very challenging shape. Notice the only thing that I have here, I got to calculate the area of this regular hexagon. The only thing I have here is the fact that I have, is that a radius or apothem? Bree, is this a radius or an apothem?
Apothem.
That's an apothem. It goes to the side. A radius would go to a vertex. Okay, so here's how that's done. Step number one, there's our formula. It's regular. I need the perimeter. I need the apothem. Well, I only got one of those. I got the apothem. I need the perimeter, right? So here's how it will be done. This is going to get complicated. I'm going to fill this whole page full of numbers. Make sure you follow along. Step number one, draw one of the radii. You don't need to draw both, but you can if you'd like. I drew both of them. Draw the radius. What we need to do is we need to figure out the perimeter. So we need to figure out what this distance right here. Well, what's going to aid us in the fact that this is an isosceles triangle. An isosceles triangle, well, if you get rid of the apothem, not only is it isosceles, it's equilateral. Why? Because it's regular. It's a regular polygon. So all the radii are equal, and all the radii equal the side length. So if I could somehow either figure out the side length right here, right? Or I could figure out, the individual pieces, parts right here, maybe using Pythagorean theorem, or maybe a little bit of trig, something like that, we could get to the answer. And that's what we're going to do. Step number one is we got to figure out the central angle of a regular polygon. Well, we know that there would be, since it's a hexagon, there would be 6 triangles to go all the way around. If there's 6 triangles, 6 sides, 6 triangles to go all the way around, well, let's see, 360 degrees divided by 6 is 60. And since the apothem cuts this angle right here in half, I'm going to erase now everything. Since that cuts that in half, 60 divided by 2 is 30. So that angle right there is 30 degrees. Why is that going to make my life easy? Because now I can either calculate the radius or I can calculate the side, either one. I'm going to choose to calculate the side. All right, so, hey, 30, well, let's see, that angle down the bottom would be 90. This is one of those special right triangles. It's a 30, 60, 90 triangle. So we can use that to get to our answer. So remember a 30, 60, 90 triangle. The side opposite 30 is x. The hypotenuse is 2x, and the long leg is 3 root x. All right, so notice here we are told on our triangle that the apothem was 9. Here is the apothem on our special right triangle. So we know that 9 is equal to 3 root x. Now we're just going to solve for x. What is that going to give me? That is going to give me this distance right here, and then I'll just double it to get the side length. All right, so let's solve for x. That means divide both sides by the square root of 3. Ooh, we can't have square root of 3 in the denominator. So we multiply the top and bottom by square root of 3. Square root of 3 times the square root of 3 is the square root of 9, which is 3, right? And 9 divided by 3 is 3. You may want to watch this video again. Watch me do that. So we just figured out that x, x is equal to 3 root 3. So this x on the bottom, this red one right here, I'm going to erase it now, can be written as 3 root 3. Okay? Well, if that's 3 root 3, then the other side is also 3 root 3. So the whole side length is double that, 6 root 3. So 6 root 3 is one side. We need the p for perimeter. So we need how many of them? 1, 2, 3, 4, 5, 6. 6 times 6 is 36. So p for perimeter would be 36 root 3. Welcome to high school geometry. Numbers are not friendly. All right, let's see. We can do this math really quick. Half of 36 is 18, and 18 times 9 is, 162. So all of that work, and yes, some of these are going to be that challenging, is 162 root 3 square units. So the steps were, from the very beginning, take what you're given, figure out the perimeter of the regular polygon. If you're not given the apothem, you also have to figure that out. Tonight's homework will be a mixture of Pythagorean theorem and a mixture of special right triangles. I think we probably need to do another one. So let's do another one. All right. So here is, let's see, how many sides here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So here's a nonagon. You have never calculated the area of a nonagon. Notice here we're not given the apothem, we're given the radius. So here's the radius. The radius is 10. So the radius is 10 here. All right, so once again, to use this formula, I need the perimeter and I need the apothem. I have neither one, I just have a radius. So we got a lot of work cut out for us right here. So a lot of work cut out for us. All right, so once again, the way you do this is you first find the central angle. Remember, the central angle is, there's 360 degrees in a circle. There's 9 sides right here. So 360 divided by 9 is 40. And this angle right here would be half of the whole thing. So that angle right there, half of 40 is 20. So that angle right there would be 20 degrees. Ooh, we don't have a special right triangle. So we're going to have to use some trig. Yes, we're going to use some trig. So notice what we want. We want to find out this distance right here, and I'll call this one y. We want to find those two distances because I need that x and then double it to find my perimeter, and I need y for the apothem. I guess maybe instead of calling it y, I could call it a. That would make more sense. All right, so we'll call this one a. All right, cool. But we're going to use some trig here. All right, let's find the x value first. Remember trig, SOHCAHTOA. I have 20 degrees. X would be the opposite. 10 would be the hypotenuse, because here's the right triangle. 10 would be the hypotenuse. X would be the opposite. Opposite over hypotenuse, that's the sine. So we're going to use sine. So sine of 20 degrees is equal to the opposite, x, over the hypotenuse, 10. Solve for x. Multiply both sides by 10. You guys have done this before. So I grab my calculators. We haven't messed with this in a while. Make sure your calculator is in degrees. We do 10 times sine 20. We get about 3.4. So I just figured out that this x here on the bottom is 3 root 4, right? Or it's 3.4. So that means both sides are 3.4. So that means one side length of my nonagon right here would be what, 6.8? There's 9 of these. 9 times 6.8 is 61.2. There's my perimeter. Now we're going to solve for a. We're going to use trig again. Notice a in relationship to angle 20 is the adjacent. So I have adjacent and I have hypotenuse. That's cosine. So adjacent over hypotenuse. The adjacent, I wrote x, but we could put an a there. So let me put an a right here. A over 10, multiply both sides by 10. So we get 10 cosine 20 is equal to a. Equal to a. All right. I just plugging things into your calculator. You plug them into your calculator. We get about 9.4. 9.4. So 9.4 is my A. Now it's just to grab your calculator and away you go. So 91.2 times 9.4, all divided by 2. And you get to your answer. There are 2 problems. I can't encourage it enough. I would play the video while you're doing the homework tonight. The process that I just showed you does not change. I gave you 2 examples, one that uses special right triangles and one that used some trig. I'm looking at the homework tonight. You got a mixture of a square, a triangle, and a hexagon. And then they basically just go through all the possibilities right there. So remember, a square, the central angle, let's see, 4 sides, 360 divided by 4 would be 90 degrees. So half of 90 would be 45. For a triangle, a regular triangle, 3 sides, 360 divided by 3 is 120. So each central angle is, let's see, 120 divided by 3. I'm confusing myself here. For a triangle, an equilateral triangle, you have 3 sides. 360 divided by 3 is 120. So each central angle would be 60 because I cut it in half. And then lastly, we did one with the hexagon. That's 360 divided by 660. Half of 60 is 30. So both for the triangle and the hexagon, you wind up with a special right triangle. And then lastly, just a reminder, we haven't done trig in a while. So here's all of your special right triangles with the appropriate sides. And here are all your trig ratios right here. Make sure that your calculator is in degrees and not radians. All right, how am I doing on time? We get out of here at 9:54. We have enough time for Bree to pick one problem. Questions 1 through 12. Pick one problem.
Let me grab my book, but I guess number 6.
Oh, I can wait for you to grab your book. And while she's doing that, just to tell you what this means, R means radius, A means apothem, P means perimeter, and capital letter A means area. All right, so she wanted to see number 6. So 6 is part of an equilateral triangle. And we're told for number 6, so here is your apothem, here is your radius. We are told on number 6 that the apothem is 4, and that's all we're told. So we need to find the other letters. So we know the apothem, we know this one. We need to find the radius, the perimeter, and the area. So step number 1, we're looking at this triangle right here. Remember, there's 360 degrees to go all the way around. So if I draw this other triangle right here, there's 3 of those in here. 360 divided by 3 would be 120. And half of 120 is 60. So this angle right here is 60 degrees. So if I draw that triangle a little bit larger, there's your 60. We need to find this distance right here. We'll call that X. And we all know the apothem is 4. And we also have to find the radius. So here's R. All right. So one at a time, it doesn't matter which one we use. Remember, for a 30, 60, 90 that looks like this, I drew that very poorly, but if we call this 30, we know the side opposite 30 is X, the side opposite 60 is X root 3, and the side opposite, or the hypotenuse, is 2X. All right. We are told that the side opposite the 30 degrees is, I'm going to erase this, is 4. So X is equal to 4 in our case. So anywhere I see an X, I can put a 4. Hey, look, radius. Radius would be equal to 2 times X. So therefore, the radius is 8. Ooh, that was easy. The radius is 8. We know we're going to do the formula for area here in a second. So area is equal to 1/2 P times A. Okay, but we found the radius. let's see, we need to find the perimeter. So we need to figure out, oh, x is 4. So this would be 4 root 3. And if I double that, I get all the way across, right? That would be one side. So if I double 4 root 3, I get 8 root 3. And there are 3 sides of this triangle. 3 times 8 is 24 root 3. That is equal to the perimeter. And now we have area is equal to 1/2. We found out the perimeter was 24 root 3. And the apothem is 4. So let's see if we can do some quick math here. Half of 24 is 12. 12 times 4 is 48. So we get 48 root 3. And that is your area for number 6. And there you go. Done, complete, and I am out of time with 30 seconds left. All right, I will say for some of you, this might be a little overwhelming. I would absolutely 100% play the video while you're doing your homework. The procedures that I just did there are the same for every one of these. The only difference is sometimes you have a square, sometimes you have this triangle, and sometimes you have a hexagon for questions 1 through 12. So the homework tonight or over a spring break is 1 through 12 all. Good luck with that. Hey, I'll have my computer on every single day. So if you ever need any help to do any of this, send me a chat. We can do a Zoom meeting. I can walk you through a couple of problems if necessary. You guys have a wonderful spring break, and I will see you in person, right, Bree?
No.
No? Okay. Well, I will see most of you back in class on the following Monday. Have a wonderful spring break.
Thank you. You too.
See ya.